So since we have quorum, all the committee members, at least I see on Zoom, I'll just finish the introducing Rakshit part. So I have known Rakshit since he took my course in spring 2020, and right after you joined our lab, and you have been looking broadly at mapping trees, and in particular our lab before you, we had not looked carefully at the Lidars, the laser scanners, and then you have gone ahead and helped us think about how to kind of position this, what are the kind of things we can do. And today in your thesis, if I understand correctly, you will tell us a little bit about what you have learned and some ways we can use this sensor, and also maybe we can have a chat about what this means for the future, precision agriculture ecology. And we are on a time crunch, so you'll do it within 40-45 minutes, and then Dr. Jiang will take the questions. We'll send all the people out, and then we'll go from there. So let me stop sharing, and I think that was the last photo. Oh, there was one more, but it's okay.
Okay, let me start sharing my screen. Is my screen visible?
Yes.
Okay. Welcome to my thesis defense, everyone. The thesis topic is real-time semantic mapping of tree topology using deep learning and multi-sensor factor graph. The committee members are Dr. Das, Dr. Martin, Dr. Throop, Dr. Zhang, and Dr. Ehsani. So the objective of this thesis is to obtain a semantic map of a tree to encode its sub-canopy topology for forestry and precision agriculture. This means that we're trying to identify major components of the tree which lie underneath the canopy and then use features from the sections underneath the canopy for forestry and precision agriculture. So some of the applications in forestry and agriculture involve estimating the DBH, which is the diameter at breast height of the trunk of the tree. And by doing so, we can estimate the total biomass of present in a tree, and then through that, by extension, the entire forest. And we can also estimate how much yield in terms of timber and wood can be obtained from the forest. From the agriculture perspective, obtaining properties of branches, such as the branch length, orientation, degree of branching, would help us identify where exactly fruits might be located, and also precisely harvest fruits from different locations on the tree. In some cases, it also helps us estimate how many fruits or flowers could grow from the tree by getting this estimate. But to enable both of these, we need to have 6 points addressed from the robotics aspect. And these are the 6 main contributions from this thesis. First off, I started by implementing a simplified scenario of the real world in simulation. And using this simplified scenario, I was able to develop the core or the baseline tree mapping algorithm. Along with this, I made a handheld setup of a sensor rig, which could be used to collect real-world data of trees, so that this collected data could then be used, could then be fed into the tree mapping algorithm to perform mapping in the real world. Once we obtain data, irrespective of whether it's from simulation or from the real world, we have 4 main stages, which is first we detect interesting features of the tree. As I mentioned, in this case, it'll be the trunk and branches that exist below the subcanopy. We parameterize these features using some kind of geometric methods or mathematical models. And once we parameterize these features, we try to aggregate all of this information from each time step as we collect all of this information. And this aggregation involves some amount of probabilistic refinement and sensor fusion. Finally, all of this is made real-time capable using C++ and other fast libraries. So the flow of today's thesis would be the introduction, setup and data, which is the simulation setup, real-world setup, and the data collected in both environments. The core mapping pipeline itself, results, conclusion, and limitations along with the future work. So before I started this thesis, the motivation behind it was that irrespective of what domain you are working in or what domain we are applying tree mapping to, there are a set of features that are of interest in that particular domain. And from those features, we collect some kind of measurements. And based on those measurements, we perform inference and obtain some kind of information or semantics. And the domains in which we collect these features in the case of tree mapping would be forestry and precision agriculture, as I mentioned. But to obtain a good sense of information from these measurements, we need to be able to identify, we need to be able to collect measurements from a large set of trees or plants so that our inferences are accurate and they're not limited to a small subset of data. And doing this data collection manually would require a lot of time and also labor, and it would be very labor intensive. So automating that using robotics would be one method by which we could simplify data collection and also estimation of these feature measurements. So that was the motivation behind the thesis. And based on that, the thesis statement itself becomes real-time semantic mapping of tree topology enables fast and precise measurement of sub-canopy tree characteristics for use in forestry and precision agriculture. So in order to address this thesis topic, these are the 4 points that we need to consider. We need to ensure that an accurate pose of the sensor suite is estimated. So we need to know where exactly we're taking measurements from using the set of sensors that I'll describe later. Once we collect some data, we need to be able to identify interesting features that will be used as information or semantics, using which we build the 3D map. We need to make sure that the Lidar scans, in this case, we're using Lidar, so Lidar scans are aligned well. Along with that, it needs to be real-time capable and GPS, and it needs to function without GPS, because if forests, in the case of forests and deserts, there would be a lot of canopy cover, which would prevent GPS signals, and also remote locations may not have accurate RTK GPS to rely on purely GPS-based navigation. One useful tool to use in order to map trees would be unmanned aerial vehicles. And that's because we can set up all these sensors on the UAV, and the UAV can move around very freely. It's height adjustable, so we can control it to go along the length and the height of the tree, and also move around to different portions of the forest by exiting and re-entering the forest in different locations based on obstructions that are there around it. For this thesis, the sensors that were selected were made such that they were UAV compatible, but within the thesis itself, only a handheld rig was used. The next section is the setup and data. First, I talked about the simulation setup and the data collected there, and then the real-world setup and the real-world data that was collected. Gazebo was used as the simulation environment, and as I mentioned earlier, a simplified scenario of the real world was first implemented in Gazebo, which means that a tree without leaves and with minimal branching structure, but varying degree of thickness in branches and different orientations of branches was constructed. These values that you see next to the branches represent the radius of each of the branches. And the trunk being the thickest was 0.5 meters, and then the topmost branch was 0.1 meters. Around this tree, a drone was flown, and this drone had the PX4 SITL simulation package embedded inside it. So we could estimate position, orientation, and basically everything else that a PX4 flight stack is capable of within the Gazebo simulation environment. The drone was mounted with the Lidar, the Velodyne VLP16 Lidar, and flown around to collect 3D data of trees. So these are 2 images of the kind of data that the drone was that the drone collected, in simulation. The same or a similar kind of setup was created in the real world, where we have a VLP Velodyne Lidar, Intel RealSense for pose estimation using visual inertial odometry. We have a Bullet M2 antenna, so that we could connect to this setup remotely and then control all the sensors from there. And it also included an Intel NUC i7, which was the main processing unit to which all the sensors were connected. All these were the total weight, including the battery that was mounted on it, came to 2.6 kilograms, which is quite which is quite common for quad rotors and hex rotors to carry. So all the sensors were UAV compatible, but for the sake of this thesis, it was only a handheld drone that was used. The two sample specimen of trees that were used were the saguaro and the palo verde. The saguaro was chosen again because of its minimal branching structure and also because it doesn't have any prominent broad leaves. All the leaves are modified into thorny spines, so they're not very prominent on the LiDAR scan and they don't obstruct the branching structure as much. The palo verde was chosen because of its much more complex branching structure and because there were a lot of leaf-based occlusions that needed to be handled. The images of saguaro is on the right, and the front and rear image of the palo verde are the ones on the left and the middle. This is a snapshot of the LiDAR scan collected from these two trees. And one thing to note is that reflections from the core trunk of the cactus or the core trunk and branches of the palo verde were much higher in intensity than the leaves. And this was very useful when training the neural network. Once we collected LiDAR scans, I also went and collected tape measures for to behave as ground truth measurements for each of the branch segments. And this was the diagram that I came up with, which basically denoted the different locations at which I collected tape measures. And the table on top gives us the GPS locations at which these two trees were present on the ASU campus. Now I move on to the core mapping pipeline. Before I get into the mapping pipeline itself, which was developed for this thesis, I'll describe a few previous works or a couple of algorithms which were used previously in order to perform navigation and also tree mapping. So traditionally, in order to map forests or to create 3D structures, 3D point clouds of trees, terrestrial LiDAR scanners were used. And this image on the right shows what a terrestrial LiDAR looks like. It's a pretty heavy object because of the metallic tripod, and also the scanner itself is quite heavy. But the way in which you collect data from terrestrial LiDARs is you place the LiDAR scanner at one location, point it towards the tree, capture a scan, and then you move around the tree, place it at a new location, capture that scan, and you go on doing that by moving this LiDAR manually to different locations while capturing scans. And sometimes it also involves the placement of alignment targets, artificial alignment targets like cubes or special shapes, which you place close to the object that you're trying to take a scan of. Once you collect all of these scans, you go back to the lab or upload them to a server where all the data is processed offline. And offline, all these scans are aligned so that you can finally get one integrated point cloud. But apart from this offline-based processing method, there are a few other real-time techniques which have been used in robotics. One of them, or one of the first few which was used, was visual inertial odometry. This involves a camera and an IMU, where from different locations along the trajectory in which the camera is moved, key frames or interesting features in the surroundings from the camera image are selected, and correspondences are found between those images. And based on the correspondences and stereo geometry, we can estimate how much the camera moves from one point to the other. And that is fused along with IMU data to get a sense of how much movement was there in the camera, and then also create, if necessary, a point cloud from it. These point clouds are generally a little more noisy, especially when moving with high angular rotations. And because it's primarily camera-based, in a scenario where we are mapping trees and there are a lot of holes and gaps in the canopy, the glare of the sun changes and lighting conditions change quite drastically, because of which the camera or the algorithm can get confused about where exactly it's located, and the pose estimate and therefore the map itself may get offset or may drift. So another technique for mapping, especially in 3D based environments, for 3D based environments, was called Lidar odometry and mapping. And this was Lidar based, as the name suggests. It helped with reducing the noise created in point clouds was much lesser because direct laser scans from Lidars were used in this case. But the main restriction for this was that it was usable mainly in urban environments because it relied on sharp edges and flat surfaces, such as flat roads and sharp edges from buildings. But it was not very usable for forest environments. So an extension on this was made using semantic loam. And this thesis utilizes ideas from semantic loam in some of the stages of the mapping pipeline, but in the remainder of the stages, it builds upon some ideas that were presented in Sloan. So coming to the actual mapping pipeline, there are 4 main stages that are involved involved in the mapping process. First is the detection of sub-canopy portions, so the trunk and prominent branches. And then from these detected sections of the tree, we have to separate each branch and trunk from each other because the neural network detects the entire section as one instance. We need to ensure that we separate them into different portions. And for each portion or for each branch that is detected, we need to parameterize them using some kind of mathematical model or geometry so that they can be represented using some numbers. And this is then fed into a GraphSlam algorithm so that we can refine these values and also aggregate them across multiple time steps. So the first step relied on training a neural network to detect sub-canopy portions of the tree. And because we're working with 3D data, this 3D point cloud data was transformed into a 2D range image representation, which is basically a spherical transformation of the 3D point cloud into a flattened image. And then that flattened image was then fed into the neural network. The ERF-net was the backbone used for this neural network. And the reason for that was because the interface of the encoder and the decoder blocks had an efficient structure due to which inference times was really high. And inference time was very important for real-time applications. And so ERF-net was chosen as the backbone. But because ERF-net was only capable of performing semantic segmentation on images, the input layer was modified slightly based on range nets ideologies, and the X, Y, and Z coordinate of each point of the point cloud, along with the intensity of the point cloud and the ring number of that point in the point cloud, were added as features to the point cloud that was fed. So on this range image, semantic segmentation was performed, and essentially similar to how you see in this image where the car is classified as a particular class, trees are classified as a different class. The network was trained to classify the sub-canopy branches and trunks as a class, and everything else to be as noise or external. The next step, once we detected the entire sub-canopy portion, was to separate the pieces into individual branches. And that again used the range image idea. So if we take a look at this 3D Lidar scan, its range image representation is the image shown at the bottom in green. We see that there's a Y-shaped structure and another branch on the left. And the same Y-shaped structure is seen here as thin black lines. And the branch on the left is another section over here on the left. So from this range image, this 2D range image, we take pairs of points from the lowest row and go along the length of the image, and then go up along the height of the image. And using a distance thresholding method, we're able to index whether a particular point on this range image belongs to a particular branch. So essentially, we go from the bottom to the top because of the nature in which trees grow and branch outward, such that trunk the trunk of the tree is index 0. And as we come across new branch instances, we label them with new indices. So the first branch would be branch 1, followed by branch 2. And then the next row would still be branch 1 and branch 2 because it's the same number of branches. And then we would say, we would start a new index such that the branches would be labeled 4 and 5 as we go on to the Y-shaped section. So given that we've identified the sub-canopy portions, separated them into smaller sections, we need to now represent them using some kind of coordinates or some kind of vector. And in this case, the method by which you can represent branches would be by using cylinders, because most branches are mainly cylindrical in structure, partially conical in some cases, but for this thesis, they were all represented as cylinders. And a vector in R7 or a 7-component vector can be used to represent cylinders in 3D space. The axis vector, which has 3 components, represents the orientation of the cylinder. The normal vector, which again has 3 components, represents where in 3D space this cylinder is located. And the normal vector is drawn from the origin all the way to the axis vector such that it's perpendicular to the axis vector. So that accounts for 6 of the 7 components from this vector that's used to represent the cylinder. The other component comes from the radius of the cylinder, the inverse of which is the curvature. And so the curvature is added as the 7th component. Using these 7 components, a cylinder can be identified uniquely in space. So every single branch can be identified uniquely within the tree. In order to, so one thing to note while parameterizing a tree is that when you collect point clouds from a branch, only a particular angle of that branch is visible because we cannot see the stuff that lies behind the branch. But even without being able to see the entire branch, we should be able to estimate the thickness of the branch and the orientation of the branch. And to do that, some kind of regression or optimization is required. And the distance metric that was used in order to perform this optimization was as given in this equation. This distance metric basically denotes how far off a point in the point cloud is from the surface of the cylinder. So if we look at the image on the left, bottom left, considering that these red points are points from the point cloud, we are trying to estimate this grayish cylinder to fit all these points such that all the points lie exactly on the surface of the cylinder. And essentially, because these points come from the surface of the branch, if we can estimate a cylinder which sits on these points, sits on the surface of these, such that the points sit on the surface of the cylinder, we end up estimating the shape and size of the branch itself. So the way that this distance metric comes about is we take a vector from the origin to the point in the point cloud, let that be Pij, and we take the normal vector from the origin to the perpendicular to the axis. Once we take the difference between those two and then calculate the cross product between that difference vector and the axis vector, we obtain a vector that lies in the radial plane of the cylinder. So it goes radially out along the cross section of the cylinder. And on subtracting the radius of the cylinder, which is nothing but the inverse of the curvature, we obtain some error metric, which is proportional to how far off this point is from the surface of the cylinder. And essentially, by minimizing this distance metric, we would be able to ensure that the cylinder that we estimate is such that all these points lie on the surface of the cylinder. And to do that, this distance metric is rewritten as below. And it's rewritten again into a more stable form so that when kappa goes to 0, or basically when really large cylinders are considered where curvature is very low, the metric doesn't go towards infinity. This optimization was performed as an unconstrained nonlinear optimization. And to do that in C++, the series solver was used, and the LM optimizer within series solver was made use of. The distance metric itself is not unconstrained, and so to convert the problem into an unconstrained problem. All the vectors, the normal vector, the axis vector, and the curvature were converted into trigonometric form, and a new basis set was obtained. And optimization on this new basis set was performed, and then reconverted to obtain the normal axis and curvature again. So these this new basis vector set will be visible in the results, and it was helpful in visualizing and making sure that the optimizer was going in the correct direction. So we've gone past 3 of the steps of the 4 in the mapping process. We've identified all the sub-canopy sections, separated them into branches, and then parameterized each of them using cylinders. The next step would be to merge them all into one unified structure so that a cohesive map is generated once we obtain readings from different orientations of the tree. And this is done using GTSAM. GTSAM is a type of graph SLAM which makes use of factor graphs. And to understand what factor graphs is, let's take a look at the diagram on the right first. So if we assume that the drone or the handheld sensor starts at x0, then moves to x1, and from there goes to x2, to x3, x4, and then so on. We represent all of these poses, or all of these locations from which sensor readings were obtained of the tree as nodes on the factor graph. So in this factor graph image at the bottom, we see that the sensor goes from x0 to x1 and so on till xn. Between each of these nodes, we add a factor which represents the odometry, or the amount of motion that existed between these two pose locations. So the amount the amount of motion that existed between x0 to x1 is encoded as a factor here. And from x1, the drone might just see the trunk. And similarly, from x2, the drone might only see the trunk. However, from x3, it might see 2 different landmarks, or 2 different branches in this case, which could be the right branch and then the right branch. And from x4, it sees the left branch and an extension of the left branch. So from each of these pose locations, we add factors to the landmarks. And the landmarks in this case represent each section of the tree, or the trunk of the tree and the branches of the tree. And in this way, we develop a graph structure and then optimize this graph in order to obtain marginalized values or optimal values for where the drone or the sensor suite actually was along this mapping trajectory. So the GTSAM graph that was used in this thesis was took this shape. X0 was the start location of the robot, or the start location of the sensor suite, which then moved to X1 and then to X2. There were 2 forms of odometry that we used. One was through visual inertial odometry, and the second was through Lidar ICP, iterative closest point. So visual inertial odometry for pose estimates was obtained from the RealSense, the stereo camera RealSense pair. And that contributed to one of the connections between X1 and X0 and X1, and similarly another connection between X1 and X2. That's the pink connection, corresponding to the motion estimate from the RealSense. Similarly, another motion estimate from Lidar point cloud from Lidar ICP was obtained, and that forms the connection between X0 and X1 and X1 and X2. From X1, if we assume that the sensor could see landmark 1 or branch number 1, then certain connections are made to landmark 1. And if it can also see landmark 2 or branch number 2, again, additional connections are made to landmark 2. And similarly, from X2, few more connections are made to L2. And these connections are explained in the next slide. So each of these connections that are made to the landmarks represent the R7 vector that was used to encode a cylinder. The red connection represents the axis of the cylinder. Green connection is used to represent the normal vector of the cylinder, and the blue is used for the curvature. The reason the blue connection is not made entirely, um, the reason the blue factor is not connected to the pose is because the curvature of a cylinder does not depend on the position or the orientation of the sensor, but only the axis and normal vectors depend on that. So it's completely independent of the pose of the sensor suite. And so it's an independent unary factor that is added to L1. So initially, what is done is each of these nodes are populated with their initial estimates. And once we run graph marginalization, essentially a maximum likelihood is performed across this entire graph to obtain the optimal values of each of these nodes. And the nodes in this case represent the pose of the robot and the landmarks or the branches of the tree. And these factors help in directing this marginalization process so that when we get the optimal values for these nodes, they have some kind of error metric to rely on to direct the optimization so that the prior values added to the node reach the desired final values. The error metrics that were used in the factors are given in these equations. It was seen that from these equations, it's seen that the axis error metric, the normal error metric, and the curvature error metric are all independent from each other because of the nature of how this is orthogonal, the matrix is orthogonal. And so we can separate each of them into their own factors and their own independent error metrics. ISAM2, the incremental smoothing graph, was used because it's not a batch optimization that needs to be performed. Instead, every time we get a new reading of a branch, the graph needs to be able to account for that new reading and then re-optimize based on this new reading that's obtained. So ISAM2 was used, and then the inbuilt Jacobian calculator was used from the post-3 GTSAM library. So that was the overall mapping process. And now I go move on to the results. Before actually trying to build the entire mapping pipeline, I first explored some commonly available LiDAR-based mapping tools or mapping algorithms. One of them was based on Loam, called Lego Loam. And this, similar to Loam, relied on the existence of a flat surface and sharp edges in the environment. So when I had just the tree present, the simulation tree present in the environment, without these 4 pillars, just the tree present in the environment and the drone flying around it, we obtained a scan as seen in the top right image. And we can see that the scan is highly drifted, or there's a lot of drift, and it's not been accumulated or integrated correctly. We can sort of identify each of the branches and trunk sections, but there's a lot of drift within the scan. So mapping was not successful using Lego Loam. However, to validate that the reason for the lack of mapping was because of the lack of sharp edges, I added these pillars artificially. And on adding those pillars artificially, we could see that the mapping for the tree was performed accurately, but only up to the height of the pillars. Once the drone lost sight of these pillars and the scan was collecting data of only the trees or only cylindrical portions of the tree, mapping was not successful. And we could see a similar kind of drift. So this kind of validated my understanding that a new kind of algorithm was required for tree mapping. And that's where some ideas were taken from Sloan, and then additional ideas about GTSAM were implemented within this thesis. So results from stage 1, which is identification of branch sections, trunk and branch sections, are as seen on the right side. The top portion of the image represents the range image in RGB space, and the lower section represents the detected tree. And we see here in the second image that the detected tree, multiple branches are detected at once. And similarly, in the third image, we see multiple branches are detected. A data set of 396 LiDAR scans were used. a batch size of 3 with 7 epochs was made use of, and a training accuracy of 96% was obtained. In order to train the encoder, a 1/8 scale representation of the range image was used, and once the encoder was trained, the decoder was then enabled, and then training of the decoder was performed. And results of separating each of these branches into independent sections, independent branches, was as seen here. Each color represents a different branch index that was provided. So the trunk was given index 0, and then the left branch was given index 1, and then the right branch green, and index 2, and so on. Similarly, there's another instance, trunk was 0, 1, 2, 3, 4, 5, and so on. Each color representing a different index or different branch segment. For each of these branch segments, cylinders were fit, and the blue vector represents the initial estimate of the axis of the cylinder. The green represents the initial estimate of the normal vector for the cylinder. And once optimization was performed, the initial estimate of the axis was corrected or optimized for, and that was represented by purple, magenta, and similarly the yellow was used as the final value of the normal vector. And we can see that irrespective of different orientations and locations of these point clouds, a good cylinder was fit for multiple branches. And a total of 10 scans were used to check the accuracy with which cylinders were fit. From these 10 scans, 24 cylinders were extracted, and a maximum radius of 0.5 centimeters was obtained, which was about 2% radius, 2% error value. And once the branch fitting or branch parameterization step was successful, multiple branches were accumulated into a single map. And so from a single scan, integrated branches, the integration of multiple branches would look like the images given here. This is the full scan, and then these are the branches fit. These are the cylinders fit to each individual branch. And then when all of these individual scans are merged together, we obtain the entire map of the tree. And the green line represents the path that the drone took. It essentially followed a quadrangle pattern until it reached this top right corner, and then moved to a higher elevation, followed another quadrangle move, and then came back to this location, moved to the next elevation or next height, followed another quadrangle and continued its mapping process. And this was the final result of the tree that was obtained in simulation. Looking at real world results, here are two scans of cylinders that were fit for the cactus. And the cylinders shown here are for the base and the right branch of the cactus. And when taken together, this is the kind of map that was generated. The gaps that are seen here are because of the branch segmentation algorithm, where transition sections have been ignored because point clouds in those regions are very different in size and shape than the actual branch itself. Some other different kind of parameterization will be required for these kinds of gaps to be filled in so that a more accurate kind of map is generated. This table again represents the values that were obtained with respect to ground truth, and all the values were close to ground truth values. These are results from the Palo Verde for the base of the Palo Verde and the right left branch. The same thing integrated would look as so. We can see there's a main branch at the bottom, right branch as seen here, left branch, and then two additional branches coming out of the right side branch. And again, the results obtained from cylinder fitting or cylinder parameterization and tape measures were close to each other with a mean error of 0.4 centimeters, less than half a centimeter, and a maximum error of 0.8 centimeters. Finally, this leads me to conclusion, the conclusion of this thesis, which is to answer this question, we can look at these 3 points that were addressed. And the first thing that we see is using this mapping pipeline, we were able to extract the axis, normal, and curvature of cylinders that were used to represent branches. And so we were able to extract a semantic representation of the tree. And by using the semantic tree representation, we essentially boil down hundreds or thousands of points of point cloud data into a few 7-component vectors that can be accumulated together to represent an entire tree structure or tree topology. And then this such data could be then used for DBH estimation, volume estimation in forestry, and then also branch position, orientation, length estimation for precision agriculture. It could also be used directly in robotics for perching or angle of approach related problems where we're trying to take samples from the tree, or we're trying to configure a drone to sit on top of a tree or sit on top of a cylindrical object. And of course, all of this was done using series and GTSAM and C++, which are all real-time capable. And so with these, with this, we can say that the thesis statement that was sought out to be answered initially was achieved. A couple of special significances or use cases of this work is that compared to prior work, we get semantics or information from the entire tree, not just the trunk and not just the DVH, but also information from branches that come out of the trunk and tertiary and 4th degree branches as well. Additionally, because of the use of branches as factors within the GTSAM graph, we do not have to rely on the existence of trees in the vicinity to accurately create tree maps, but we can work to map isolated or individual trees. And that's very helpful if you are trying to map trees in a savanna or in where trees are very isolated from each other and there's no adjacent tree that we could rely on as landmarks for landmarks. Similarly, in cases where there's a lot of undergrowth and occlusion between trees, having this kind of graph-based refinement would help us map a tree without having to rely on adjacent trees because of undergrowth and drooping canopy that covers adjacent trees from the current tree that's visible. Along with that added advantage of being able to map individual trees, the feature of GraphSlam, which is to be able to consistently refine landmarks and pose values, is of course always available. So some of the limitations that exist in this are that if we have a really long cylindrical trunk structure, and when we consider the LiDAR scan obtained at location X1 and X2, the LiDAR scan seems the same from both position X1 and X2. And because of this, trying to localize the sensor suite or trying to localize the location, trying to obtain the location from which these scans were obtained is quite difficult. However, in most trees, trunks are not completely parallel to each other, and because of their branching out and fanning out nature and some amount of randomness, this kind of problem should not occur unless it's a very, very tall tree with highly minimal branching, like sequoias or something of that sort. Another kind of issue that could appear is that cylinder parameterization does not account for the endpoints of the cylinder. So without having an external script to monitor endpoints or to keep track of cylinder endpoints, if two branches were collinear with each other, so a branch on the left and a branch on the right were along the same axis, when a scan from the left side of the tree is obtained, this branch would be identical as the branch when looked at from the right side. And this can cause confusion with the algorithm in terms of where the robot is. But again, as long as multiple branches are visible at a given instant of time, this should not have much of an effect on the mapping pipeline. And a third issue would be the diverging nature of Lidar, wherein if we try to map a tree from very far off, because of dispersion in Lidar rays, a lot of the branches might be missed out entirely. However, if we get really close to the tree and try to create maps from very close by, then we would only obtain readings from a single branch, which would prevent GTSAM from obtaining good estimates by making use of multiple branches at the same time. So this kind of adaptive distance thresholding needs to be worked on, so that it can perform well irrespective of the distance from the branch. In terms of future work, the first point is adaptive distance thresholding, so that basically irrespective of how far off we are from the tree, we can identify the number of branches correctly and also make use of GTSAM well enough. Adding RTK GPS as a unary factor would be helpful in order to georeference the data better. Right now, the prior pose is just taken as 0, 0, 0, but adding GPS-based factors would also be helpful. We could also incorporate additional odometry values as suggested in Sloan, as suggested in the Sloan paper. We could use more, we could basically use a higher density LiDAR so that even smaller branches could be picked up, and not just the prominent branches are the ones that are used in the mapping process. And right now we spoke about only the sub-canopy portions, but using techniques like alpha shapes and convex hulls and concave hulls, we can draw bounding volumes around the canopy as seen here. And we could somehow work on parameterizing that as well in terms of, in order to be able to map the canopy also. And for this, the final point, of course, being this thesis was only tested on a few trees, one in simulation and then 2 in real world, but a lot more work would be required to make this extensible and usable for any kind of tree and in many more situations. And yeah, this brings me to the acknowledgement section, where I would like to thank all the committee members for giving me a lot of help and guidance while working on this thesis and while writing the report as well. I got a really good, wholesome experience from this, where my master's was not just courses based, and I was able to explore a lot more with a lot more hands-on and practical applications. And of course, the lab members with whom I had a lot of technical discussions and yeah, basically helped me out on a day-to-day basis. Yeah, that concludes my thesis presentation.
Thanks, Rakshit. So what we will do is, normally we would take questions from the audience, but in the interest of time, we would let Dr. Jiang first ask his questions. Would you like to do this in public, or should we make this private at this point? What do you think, Dr. Jiang?
Yeah, I think public is perfectly fine.
Okay.
Yeah. So and thank you, JD, and then all the other committee members for accommodating my time constraint. Appreciate that. So congratulations, Rakshit. I think this is a very good presentation, very comprehensive work. Nicely done. Good job. I only have a couple more of a clarifying questions. The first one is, according to your sort of a statement, you want to do all these in real time, right? I saw real time as the first word in your problem statement. Right. Could you comment on the real time performance of your entire pipeline? I'm asking this especially because in this case, I understand that everything is probably processed offline. But I was just thinking, you know, if you really put a LiDAR on the drone, right, and you probably have to, you will, you know, fly the drone in the pattern that you showed on one of the slides. And I do think real-time processing of this LiDAR image is very helpful because it also helps you figure out if you have, yeah, exactly this page, thank you. The real-time processing will also help you figure out if the raw data you collect so far is sufficient for you to build a tree map, right? So I want you to comment on the real-time performance of your algorithm at this point.
Right. So in terms of performing this offline, part of it is correct and part of it is also sort of still real time. So when I ran my algorithm, I didn't run it on the sensor suite itself, but instead I ran it on my laptop. But the algorithm was run using ROS bags, so recorded data which was played back in real time. And the configurations of my laptop was quite similar to that of an Intel NUC, which is that it had 16 GB of RAM and it also had i7. So while running continuous streams of data, it was able to build this map as data was incoming. I've not run any specific timing analysis for different components or different stages of the algorithm to see exactly how much time each of them consume or how much memory each of them consume, which would, I guess, also be important to run when we're trying to deploy it on an actual drone, because we would have other things running on the drone, like actual navigation related processing. So it is real-time capable in terms of running this solely by itself, because it's able to process all of this data as the ROS bag plays. However, I've not actually tested it with other navigation or control related algorithms running in parallel.
Of course, yeah. Thanks for clarifying that. I think this is great, but I guess it will be helpful for you to you know, at least comment on this and then mention that this is done in I'm implementing this in a reasonable processing unit that is similar to what can be done on an onboard drone, right? Yeah. So, and of course, I'm very happy to hear that you comment on that. You know, when you have a drone there, the part of the processing capability needs to be used to actually control the drone, plan the drone, and then do that, right? So, so of course, further testing may be needed, and I think that will be very helpful to sort of echo back your real-time statement. Okay, so this is the first one. Second one is I noticed that as the first stage of your processing, you're trying to, I remember, detect the sub-canopy. You mentioned a neural network you trained. I'm trying to understand, is that neural network specific to a type of tree, or for, you know, for different trees you can pretty much use the same type of neural network? And then, of course, I understand if you have a huge amount of data, you might be able to, you know, work it for any trees, but I'm just trying to understand for the one that you are trained right now, is that specific to the tree you're working on?
Yeah, so one of the input layers that changes specifically with respect to the tree would be the intensity value. So intensity values for a cactus, because it has a lot more water inside it, and the amount of absorption for a cactus is much more different from that of a hardwood tree like a palo verde. That value would change at the input. So inference would have to change accordingly. So additional training would be required specifically toward cacti or specifically toward other hardwood trees. The other aspect would be, of course, just broad scale training, because XYZ and it's the network's ability to infer what a branch is and the shape of a branch based on the XYZ values of points would just be dependent on the shape of the tree. So this these are the two main directions in which the training of the neural network would affect the kind of inference that comes out of the network.
Right. So I guess in summary, it sounds to me that if you train this neural net, and you may have to retrain it if you're applying this algorithm into a different type of tree.
Yeah, correct.
Does it sound right? Okay, yeah. So that's what I figured, but I think it's helpful for you to just make it clear in the thesis, so people know how to apply this. The next question, can I ask another question?
Yeah, I think that's fine. Like, I don't think so. It's 1:57. You can take another 3 minutes if you need or more.
Okay.
We have to leave at that point. Yeah.
Okay. Yeah, I will just ask one more question. This could be a quite naive question. I understand, Rakshas, you were using this Lidar to do the tree mapping, and I think you also mentioned several other types of approaches, including visual odometry and all that. Yeah. So have you compared your work, including, for example, accuracy, computational load, with some sort of, I would probably think one of the most common one is visual inertial odometry. Have you compared the pros and cons of your approach in general with that? Because I suppose when you say I'm trying to build a tree map, most people would directly think of, okay, I'm going to use a camera, right? Mm-hmm. So what are the pros and cons when you compare with this approach in particular?
So the visual inertial odometry, I think, has become a very mature algorithm at this point. So when you consider the real sense, it hardly uses any power, and it does all the VIO processes inbuilt, and it's a really tiny package. So comparing it with comparing LiDAR-based processing with visual inertial odometry at this point in time may not be a fair comparison, just because of the level of optimization that's happened on the VIO algorithms and how they've been able to embed those algorithms directly onto embedded systems and low-level processors. But from a performance standpoint, like in terms of an application standpoint, I think the main benefit we get between using LiDAR and visual odometry would be that you don't have to depend on light in order to map. So if you had to go in a really dense forest where a lot of light changes would happen, or because of breaks in the canopy and openings in the canopy, or depending on the orientation of the drone, if you were trying to look upward a little bit, depending on the direction and orientation at which you're looking upward, glare from the sun would also kind of add to drift. And I saw this while I was collecting data as well. When I had only VIO data at one particular location while collecting data from the Palo Verde, sensor values would jump by about 15-20 meters, and then it would start localizing around that new 15-20 meter offset location. And so those kinds of details can be avoided. And ideally, merging both LiDAR-based odometry and VIO, which is what GTSAM does in this case, would be a good approach, is what I think.
Okay, sounds good. I think that's I guess that could also be helpful to include and then comment on and of course it's very intuitive that usually visual approaches probably doesn't work at the dark nights or very under sun glare, but just to make the comparison very comprehensive, I guess will help the general audience as well.
Okay. Yeah.
Okay. I think that's pretty much all I have. I just want to say again, congratulations. This is really great work. And just let me know if you need help on anything, when you're trying to extend this work. Okay.
Yeah.
And Dr. Das, I'm gonna give this back to you. And
just send me an email with your decision. Although you said congratulations, I'm hoping for the best, but you can just send me a private email after.
Absolutely. Okay. Thank you so much. Thank you, Rakshas, and thank you, JD. And
thank you, Dr.
I'll talk with you guys later.
Yeah.
Yep.
Thanks.
All right. So bye, Dr. Jiang. So we'll open it up for how should we do this? Robin, Heather, Reza, continue with maybe odd questions from committee members. Who wants to go next?
Or do the public?
We could do public now. Yeah, let's do that.
Yeah.
Public questions, just unmute and ask or type it in.
I guess I can have a question first. So let's work, Rakshit. I have one or two questions depending on the time. So first one is like, what's the frequency of your data sampling? Because you mentioned it's data fusion, and I assume if you fuse all data you received, then the graph, the factor graph you are building will grow rapidly, and it will become very large, and it will probably also add a burden to computing.
So in this case, I'm only adding factors. So the LiDAR is working at 10 Hertz, while the IMU or the VIO outputs are coming in at 50 Hertz. And the IMU itself was working at 200 Hertz, but I was only adding factors whenever both the LiDAR scan and the VIO input were coming in. So essentially at a maximum of 10 Hertz and slightly possibly lesser than that. Ideally, we would have to take a look at how to optimally maintain the graph and also remove old nodes so that you're able to add nodes frequently enough so that there's good optimization, but at the same time, it doesn't grow too large and become higher than 1 million nodes in size.
Sounds good. Another question is maybe similar to Dr. Zhang's question before. So do you observe any like visual odometry improvement by integrating SLAM?
Yeah, so the by integrating what exactly?
Yeah, for example, like when you use semantic SLAM of the trees, do you observe any improvement, odometry improvement by comparing with visual initial odometry? Like like real sense tracking camera.
Correct, yes. So because this relies on ICP also, so one of the pose estimates between branches, between poses is ICP, and ICP is an expensive operation, so you cannot perform it on the entire point cloud, otherwise it won't become a real time. I'm performing ICP only on the identified sub-canopy sections. So just on these yellow portions or just the wooden branch, woody sections, I'm using ICP there. So adding ICP along with VIO would kind of balance out any issues that VIO has. So that is the reason 2 modes of odometry were used.
Yeah. I would also.
Sorry, go ahead.
I would suggest that you probably like add a performance comparison or evaluation, when you add an ICP or when you add other landscape SLAM, and how the performance will be improved, like some performance metrics.
Okay. Yes. Yeah.
And maybe something Xiang can help with for our paper that needs to be written on this.
Yeah.
Good suggestion, Xiang.
Yeah, that's all my question. Thank you.
Yeah.
All right. Going 1, 2, 3. Audience. Cole, anything you wanted to ask? Cool. Let's move on to committee members back. Who wants to go first? External member, Reza, did you have anything to ask?
Sure. Thank you, Rakshit. That was a great presentation. I have a couple of questions. One is related to real time. I'm thinking about why do you think that real time is so important to do this? It seems for many applications, you can collect the data, do a post-processing, at least in agriculture, and use that later on. So what is the real practical problem, as like previous person asked this question relating the size of data? And if you try to collect this on a large orchard, pretty quickly you start to develop creating files which is huge in size. And I was thinking, if you're trying to do something real time, the best way is to try to reduce your data or remove the unused, basically collect only useful data and get rid of the data that are not useful for your application. That will probably more useful than trying to do everything in real time. The other question I have is mainly related to, I saw you're using a 3D LiDAR, and still I'm not understand why did you suggest to move in a pattern around the trees? Do you think that just collecting at one side is enough data? If you just move from one side of the tree, does it give you enough data rather than trying to move around the tree? Because for agricultural applications, it's really not practical to move around the trees because trees are in the row and usually the canopy in touch, you can actually fly around them.
Right.
So wondering, why do you need to go that, I mean, with the 3D laser, is not enough field of view for you to just collect in one pass rather than trying to move in the path that you showed in your pictures. So
Yeah.
wondering, why do you need to move like that? And basically, I can understand that for the large, tall trees, you may need to do this, but is that the reason for it, or there's other reason that you need to move like that?
Right. So addressing the first question, so the idea of doing this, bringing about real-time computation is not absolutely necessary. It can still be done offline. We could record the data and then take it back to a server or lab and then analyze it and perform, create the map offline. But the main advantage of having it real-time would be in case we had other requirements to meet. For example, if we were trying to explore a forest or trying to decide which branch to perch on, or which branch to make the drone sit on, or from which branch we need to collect a sample from. In those cases, creating the map of the tree live would help us understand where exactly the drone is and then what kind of features we are going towards, and then basically refine our path and trajectory and make more intelligent decisions on the spot. So that's why real-time was emphasized, I guess, in the thesis, but it's not a mandate or it's not absolutely required in order to map trees. And then going to the second question, it is possible to use only one planar view of trees, as is the requirement for agriculture. It's not again not necessary to go in spirals, because when we look at the branch parameterization algorithm, and we see that actually, let me bring up a different slide. Yeah, so here we see that the red points are actually the Lidar that the drone sees, whereas it only represents a portion of the cylinder which is visible from the Lidar. So if this axis was where the sensor was present, and this was where the actual branch of the tree was located. Similarly, this is where the sensor was located and the actual tree branch was present here. Only a portion of the cylinder was identified, or we got reflections of Lidar only from a portion of the tree, but still the optimization for the cylinder was able to estimate the entire cylinder thickness accurately, or at least up to the 2% error that I mentioned. So it is possible to do it only in one direction, but if we were trying to build much more accurate models of trees, wherein sometimes trees may not be perfectly cylindrical and they may be oblique, and there may be kind of weirder shapes and bumps. And if we were trying to take care of those aspects as well by using maybe cylinders or maybe kind of elliptical cylinders and maybe a little more complex shapes, then being able to circle around the tree would be required. But a reasonably good estimate is possible just by getting the planar structure.
Thank you. I think your work is really very useful for applications in agriculture. You mentioned as a harvesting as a potential application, but I believe that actually the biggest application of this is in pruning. When we need to map the tree and then decide where to make those cuts. So for a pruning robot, this will be the absolute requirement and needed thing. So your work definitely can contribute to that.
Okay, yeah, I'll add pruning to one of the application aspects in my report. Yeah.
Thank you. I think I don't have any other questions.
Thank you, Dr. Ehsan.
Thanks, Reza, and we can. I'll be talking to you more to kind of think about the next steps for this. One of which will be moving our sensor suite along a row of trees, like you just said, and taking Rakshit's work to the next step. All right, other committee members, Heather, Robin.
Sure, I have a few questions. First of all, great job, Rakshit. I really I enjoyed reading your thesis, and you gave a great presentation. So congratulations for that.
Thank you.
And so I have just some general questions, thinking largely about applications. Some of these ideas have come up in one way or another already. I think the pruning aspect is really interesting. Are there other ways that you can imagine, from the information that you have now, are there aspects of this technique that could be applied fairly quickly to particular problems in agriculture or forestry? What do you think along those lines?
I think one point that comes to mind that comes up front to me is biomass estimation. So Dr. Martin was asking me to go through Chavez' paper, Jeremy Chavez' paper, where they build inference models to estimate the amount of basically estimate biomass based on tree shapes, DBH, and few other parameters. And then they only looked at basic measurements from the trunk, and they didn't make it did not directly make use of measurements from other portions of the tree. It only used trunk or height values and a few other basic measurements. And then it was kind of generalized by using 2,000 or 4,000 trees in the equatorial region. But because again, trees are very different in shape and size, and maybe non-equatorial trees may have slightly different shapes and sizes and things like that. Accounting for other branching structures may also change these estimates that we have. It might give us better estimates, or it may end up matching the estimates that have already been provided. So that's one that comes to mind immediately. But then I remember that you were also working on litter estimate. You were working on litter. So if we could perform this canopy volume estimation, maybe there something along the lines of how many leaves are present on the tree and then how much it could shed. That could also be an application, but for that we'll have to actually map the canopy itself, which has not been done. But there were some ideas about using alpha shapes and then planar geometry, which could be useful in characterizing volume of canopy and things like that.
Yeah, and I think like the biomass application could potentially be really important, right? Because that's so critical in terms of trying to understand how much tree biomass is there, which is so critical for understanding how much carbon is there as we try to understand climate change impacts. Let's see. Oh yeah. So it seems like a challenge then in terms of applying this is scaling it, right? So are there like key steps forward that you think would be most important to make this scalable, so that instead of thinking of individual trees, one could be thinking of the whole forest?
I think the first step to scaling it would be trying it on a longer span of data to see how the graph that the GTSAM graph that I mentioned actually grows with time, so that we could see whether computationally and memory-wise there's sufficient space. There was another UPenn group which I was talking to earlier called TreeFo. It's now called TreeSwift, and they are essentially doing this on large scale now. They were the developers of the Sloan paper initially about a year and a half ago, and then now they've got a company behind it, and they're doing this at a much larger scale for forestry. And they were saying that their current status is they're able to collect data for about 100,000 to 300,000 trees, and that's mainly to estimate DBH and to get plantation trees where branching is minimal and we have really long, tall trees. And that's using current standards of SSDs and data compression and things like that. But in their technique, they did not use GTSAM, so I'm not really sure how it scales up. But that's where I see I guess that's where the limit is right now. But I haven't really thought about how I would, what changes I would make personally in this project to allow it to make to be expandable on a large scale.
Okay. And then sort of shifting gears a little bit. So if you've approached this thinking about trees or a cactus, are there other applications that you can imagine that have nothing to do with plants, right? What else could one do with this approach that you've developed?
Because we're using cylinders as the primary, I guess, representation structure, by changing that representation structure to maybe cones or spheres, we could expand this to other applications, depending on the shape of the object. But using just cylinders, I guess, mapping or modeling bridges or pipelines in certain locations could come to mind. I'm not sure. A lot of work there uses cameras to identify cracks and to identify leaks and damages, which are very minute, and you can't really pick that up by representing the entire cylinder. But possibly there are places where you need to use these cylindrical representations to aid with navigation and localization. This pipeline could be used, but then the actual identification of issues could rely on the camera input. So I guess maybe bridges, telephone wires are too small, I guess, but somewhere where cylinders come into the picture is what I can think of on the spot.
Cool.
Statues.
Yeah. And
Yeah,
what's that?
I said human statues, you know.
Well, and I love that it's focused on trees. I mean, there's my bias, but right. And so often we end up, using some technology that was developed on something else. So nice to have this, tree focused and that you're thinking about it really from that perspective. Great.
There was the paper that helped me, the paper which I referred to come up, which gave me this error metric for cylinders, also had error metrics for to fit spheres, conical structures, toruses, so basically donuts, those kinds of 3D structures on point clouds. So basically looking into how they've come up with this distance metric by seeing how far off points are from the surface, we could expand this into any other shape as long as we have a geometric representation for that shape that we're trying to fit towards.
Great, thank you. That covers my questions.
Thanks, Heather. Now, Robin.
I think most of the questions were really covered, and I'm really impressed. I think it's a big leap to go from, like you say, buildings and roads and these very angular shapes to something that is unconstrained. And this is the challenge that we have always had in ecology, and I'm just grateful that you took it on. And yeah, the biomass estimation, like I could also see if we could get an underwater version of this working somehow. We could measure corals, and just there are infinite possibilities, I think. And the fact that, well, and that's the other aspect that's good, is that because you're not relying on GPS, you could use it underwater. But also, like you say, savanna systems and things like that, where you have very isolated canopies and things, but also being able to get under the canopy and make measurements that are realistic without light or having the light shade problem, and that you would have by using just photogrammetry is really important too. So yeah, I think it's an amazing first step, and you got through many of the challenges and thought processes that get us along that path. So yeah, very impressed. I mean, my questions were all kind of answered by other people, getting it to be more area and Just other ones I kind of put in your thesis themselves, like what exactly was the error and little things like that, but nothing major. I just am impressed and I learned a lot working with you. So
Thank you.
thanks.
I think JD was mentioning that we might consider mounting the LiDAR vertically instead of horizontally. And having it vertically, I think, would help a lot more in getting underneath the canopy and then seeing how it is for branches below leaf cover once we get below the tree. So that shift, that would require changes in the second stage of the algorithm. But if we can identify some way to implement the second stage of separating branches, even when the LiDAR is rotated, we'll get a lot more information from trees because trees are mainly horizontal. And also, I think this under canopy, exactly under leaves, those kind of structures would also start to stand out if we turned the LiDAR.
That was one of my questions because I don't understand all of this totally, but if you did, so you said you went from the bottom to the top of the tree, but can you use that data and then go the opposite way so that you would learn? Because I think that would help with some of your column problems and the opposite, the unending branch problems. Like if you do up and then down, but you can use the information from your initial scan in your second scan.
That is mainly handled by the graph portion, where it figures out which is the closest related branch, and it's able to either consider that branch as a match, or it kind of ignores it from there. But yeah, that is possible using the graph portion of it.
But it keeps track of like
everything,
many steps back. So okay.
There are ways to prune it also. So once it reaches a certain stage, it starts to ignore older values, but I haven't explored that because I haven't explored such a large problem, and I haven't had to prune any of the nodes from the graph.
Cool. So I was actually walking into the lab, and this is how the new setup is. So it's on the trike already, and so everything is functional right now, Rakshit. So I have 3 quick questions. One thought was that we could turn the LiDAR, but then we have to find out how dependent you are to the ring physics of the orientation. So are there some details there that we need to address? Like how well can we be? How agnostic can we be to the orientation of the LiDAR? What if we start spinning the LiDAR, which is becoming common, but then maybe the power unit has to be set? Will it involve a lot of change for your algorithm? That's kind of my first main question. And added to that, what if we have to map routes? If your point cloud came from another mechanism altogether, let's say it was photogrammetry with a very good camera, so that you won't have the LiDAR ring kind of thing. What does it mean? I think they're kind of related, right? The two questions.
So I think both of them go to us not relying on this ring or layered structure of the LiDAR point cloud, and it makes us it requires us to identify branches from unstructured point clouds where we don't have these layerings, and we cannot rely on the ring number to go from bottom up and identify branches as we separate. Right. So I think there are other algorithms which exist which do this, but I'm not sure how well they would perform, and I've not actually explored them. But something which explores skeletal structure identification, so that it's able to see how, so that it's able to essentially take surrounding points into consideration, find the average, and kind of get the average or the center point of all of these cylindrical branch sort of kind of structures, and then build along its length. I think there are algorithms which exist like that, but it's not something I've explored properly.
So you're saying that it should be possible to only one module in your pipeline could be updated, and then the second detail will be that instead of a 7-dimensional feature vector. You will have a 6-dimensional feature vector. The radius won't be important anymore. So you'll be thinking in terms of a skeletal structure of your root initially, rather than thinking about the diameters of the roots, which will be a harder problem.
Diameter could still be included if we identify sections correctly. That's just a separate component. So once we identify which points of the cloud belong to a cylinder or belong to a branch, we could estimate the diameter quite easily. But identifying these separate branches so that we can say that this is the beginning of one branch, this is the beginning of a second branch, I think that would be that section, stage 2, basically would have to be changed.
Okay. So what I'm hearing then is, even with right now, and then some of the changes, Rakshit, we made based on your advice was making all the lenses inline and ensuring that like all the distances are kind of multiples of 5 centimeter. And of course, we could do that because in between when we last met and now we can weld aluminum.
Yeah.
So it's just easier. But we will start collecting data. I'm hoping that we can start kind of on campus, just see how things turn out. Now, of course, you already have a job. We'll have to discuss if some of my students need your help. But I think those were my questions, and thanks for introducing factor graphs with some rigor to us.
Yeah.
I think this has been really helpful. So that was it from me. So what do we do now? I think we sent Cole out, Rakshit out, have a chat and decide. Is that the plan? Heather, perfect. All right, Rakshit, let's see. How do I do this? Waiting room, it's your call, right? So you have to make one of us a host or co-host.
Okay, I can make one of you.
And then we have to send you to a waiting room. I'll go back to my office. Actually, let me move the trike out of the way. Right.
Should I stop the recording? How does this work?
Yeah,
Yes.
Because otherwise you will know what we spoke about.
I've stopped the recording and I'm making JD the co-host. JD, I think you are the co-host. No?
Perfect. So now let's see.
And he might need to be the full host. I think I've had this problem where co-host still can't send you out.
Okay.
Yeah, I have to be the host, actually.
I see. Okay. Yeah. Okay, you're the host now.
And then I have to send you to the waiting room.
Okay. Yeah.
Let's see. Assign. Put in waiting room. Bye. See you next year.